Good morning on the day 4 of the 6th drug design workshop. And today we will be focusing on a structural drug design approaches. And all of those approaches are based on the molecular modeling. And that's the reason why we are starting with the molecular modeling basics, just to go through how the interactions are there and how they are important for the drug design. So Albert Einstein once said, a theory is something nobody believes except the person who made it. And the experiment is something everybody believes except the person who made it. And if you think about it, and if you've been through some kind of a labs, you know that it's true. So since we are on the side of the theory, let's move into what we actually can describe and what methods. Because when we are looking for the chemistry, we are actually scaling up the matter and time, because we cannot use the same theory in order to basically look for the electrons within the atom and also whole ribozyme or whole cell. We have to use different methods which are scalable for that specific purpose. And also for the time beings, if we want to calculate with how the electrons are moving, we need to go extremely fast. We have to be speaking about the attoseconds. But usually when we are speaking about how the molecules move, we are speaking about the nanoseconds or even microseconds. Yeah. So those scales are quite large and largely different. And for that reason, we have to think about different methods that can be used for description of those things. So here in the real world, we can use our eye. But unfortunately, we cannot go lower in the time scale. And we cannot go lower with the size. The last thing which we are able to see are basically nanoparticles which are in the solution, and we can see them as some small opalescent dots, and that's the limit of the human eye. But those nanoparticles are at this scale, so it's still beyond what we are usually able to show with the molecular dynamic simulation, for instance. And for those type of the systems, we have to use a coarse-grained molecular dynamic simulations at the different levels. And the tuning up the atomistic simulation with coarse-grain is quite an interesting field of biophysics. But this is usually the level which we are not really needing for the drug design. For drug design, we are interested in the systems of the proteins and, let's say, RNA, approximately 10 to the 4th and to the 5th number of atoms. Small molecules are, of course, much smaller, so usually up to 100 atoms, much more oftenly, much less. But this is the limits which we can use. So for those parts, we can use either molecular mechanics, when one of those things are basically afterwards molecular docking as well, which is using those techniques, or we can use towards the molecular dynamic simulations. For instance, we can dock and then use the molecular dynamic simulations to refine the binding poses, as you will see in today's afternoon's tutorial. Am I right? Yeah. Okay. So, but all of those things, how individual atoms are interacting, is governed by the molecular interactions. Molecular interactions are basically of two different types, covalent and non-covalent. They have quite different origins. So the covalent one are sharing the electrons by the bond. And that's the reason what is making the covalent interactions much stronger. And we are usually speaking about them as bonds because they are strong enough. Non-covalent interactions are based by the electrostatic interactions between individual particles. And those electrostatic interactions, there can be different types of the electrostatic interactions. It can be like charge-charge, or it can be two seemingly neutral atoms. But we have to think about that the electrons within those atoms are moving and therefore are making induced dipoles that are making the interaction strength. The major difference between those two types of interactions is their strength. Covalent interactions is usually approximately like 400 nanojoules per mole, kilojoules per mole, and they are shorter as well. They are usually about 1.5 angstroms. Non-covalent interactions are much weaker, like 20 kilojoules per mole, and they are further, so from 2 to 5 angstrom. Usually when something is further than 5 angstroms, we are thinking about it that it's not really interacting any longer. And how those things are moving is a key property. So in general, majority of molecular mechanics is based on the idea that the total energy of the system is a function of individual atom positions and how they interact via those interactions. So we take the function of all positions and we take the covalent and non-covalent interactions energies. The covalent ones is how the atoms are bound to each other. So this is the first bonding, and how then the angle and the dihedral. That's the last part. Then the non-covalence is the electrostatics, which is usually stated as a Coulombic ones, and van der Waals. And all of these are usually somehow connected to each other, and those bonds, a little bit bigger than I've expected, are moving along, let's say, some kind of a harmonic potential, where there is the optimal distance, and how much it will go further is driven by the force constant there. When we put all the others, we can have a function for every interactions that's defined like this, and those in total is making me the energy. So here are just a short overview about what is usually used in order to describe those interactions according to the position, their typical position, and usually some kind of a force constant. In the case of those bonding ones, the electrostatics is depending on the distance and the charges of individual atoms. And since we are speaking about the atoms as balls on springs, then we usually add the whole electron density of that specific atom, and we are usually putting it together as one so-called partial charge. And this is coming to this equation. And the van der Waals is basically taking the repulsive part and attractive part of the diffusion and is usually taking it together into this Lennard-Jones potential. So the covalent interactions, the covalent bond is given by the overlap of the electron orbitals, and it gives the really strong interaction, and its distance is usually around here, and the actual function that is describing it in comparison to the one which is used in molecular mechanics is actually there is a high repulsive part which is coming from the Pauli repulsion. And this one is actually not steeper than the harmonic potential which is normally used. And this one can lead towards the separation. So it's not going towards the positive values as well. So, but this type of the function will be calculated quite slowly. And since we want to use for a quick calculations, we are using a harmonic approximation of the spring for this region mainly. And this usually works well when we are basically looking for a stable organic molecules in their normal temperatures and normal behavior. But since we are using harmonic approximation, we have a large problem here that it does not dissociate by themselves by the typical definition of the force field. So if you need something that would be making the bonds and dissociating them, you have to go into different methods like quantum mechanics, which is able to basically take the bond apart. The important part is that individual bond types usually have a specified bond distance, which we can measure via X-ray, and force constant, which we can get from the infrared spectroscopy. So these two experimental techniques can be used to give us basically what is the strength of the bond in an individual molecule. And we can take this in order to set up that, okay, the bond between the hydrogen and chlorine will be always like this. And therefore we can gather the similar bonds in similar approaches and basically take them as a transferable parameters and form some kind of systems called force fields, which is basically a combination of the equation which is used for calculation of the energy for the positions, those parameters for those equations for individual atom types, and other parameters like the time step, which is usable and how it should be used with another methods. So yeah, the angle bending usually is described by quite similar equation as the bond, so it's usually quite easy. But the torsion dihedrals are usually quite problematic. And the major reason why the torsion angles are problematic is that these two, well, let's say 4, 1, 2, 3, 4. So, well, this hydrogen and this hydrogen are connected via the torsion angle, which is in their case 0. And there is also a dispersion interaction between these two hydrogens. And when you are developing a force field, it's usually quite problematic to entangle these two parts of the interaction, because both are important. And for that reason, usually what's done is that for these 1 to 4 atoms, you basically use everything as a torsion angle. And you basically say that for this pair, you don't calculate the dispersion interaction at all. And in that case, you basically have the value of both of them given into the torsion angle. Similarly, improper torsion is basically looking for how the molecule should be straight. For the non-covalent interactions, I have a quote from my former supervisor, Professor Hobza, whose whole professional life he spent on quantum chemical analysis of non-covalent interactions. And he says in his book, not despite the weakness, but because of weakness, the non-covalent interaction play a key role in biodisciplines. And that's actually quite true, because the non-covalent interactions, in comparison to the covalent ones, are weak enough so they can form some kind of a recognition complex, and this complex can be then dissolved again quite easily. So it is quite important interactions for the molecular recognition. and for whole macromolecular structures and functions. Yeah. And molecular recognition is the basic for the drug design, because we are basically trying to find some drug that would use molecular recognition for that specific target. So, what types of the non-covalent interactions there is? If you will look into the literature, there is plenty of types that are described in there. Hydrogen bonding, halogen bonding, this London dispersion, hydrophobic interactions, and I don't know what not. But in general, if you look into the basics about how those interactions are formed, you came up at the end into these four. The first one is electrostatic. You have two permanent multipoles. And depending on what type of multipole it is, if it's monopole like a charge or dipole like a water, then it's different in the strength. The most strong interaction is, of course, monopole to charges. And it goes quite steep. And it actually is going towards quite large distances. So if you have something charged in vacuum, it will interact with almost 100 angstroms. Still understandable. But if it will be in water, there is another interactions coming in, and that's the induction. The induction means that you basically move and you react to the charge by inducing of the dipolization or multipolization, let's say, on the new compound. And this multipole will basically weaken the further interactions from the charge. And that's what's happening in water, because if you have a charge in water, then the water will accommodate that charge, and therefore it will ease out the interaction and weak out the interaction further. There are two things that happen afterwards. And the first one thing is that each ion, if it's in the water, has some kind of hydration shell. And if the ion is, let's say, polyvalent, like zinc ion or magnesium, for instance, for ATP, then it usually has a second hydration layer as well, because it's strong enough to form the water. One thing which is making that afterwards is that the ion, if it's together with those waters, it's moving as one object, so it's much heavier at the end, experimentally, and also in the simulations. Because in the simulation, if it would be just one single atom, which would be moving, then it would be much quicker than the ion together with whole waters around it. So it's necessary to think about it when you started thinking about the solubilization of stuff. That's all. And then there is a London dispersion. London dispersion is coming from the fact that we have two neutral molecules, and those two neutral molecules have to have electrons which are interacting to each other. So each electron is attracted to the nuclei on both sides, but it's repulsed by the electrons on the other atom. So they are starting to be their movements are correlated, and as such, they are then attracting each other. So that's the London dispersion. Of course, they are interacting only towards the electron, which is just from the next atom. So this is extremely close interaction, only when the atoms are actually in a contact. And you would think that those tiny changes of the movement of the electrons are really weak, which is true, but there are plenty. Because you have this interaction is coming from every atom towards every atom. And therefore, this is holding water together and all liquids. Basically, this is the interaction which is holding them at the end together. And even though it's really tiny per one atom, it can cover, for instance, that you will have two flat atoms interacting to each other, and two molecules interacting to each other, and their interaction will be therefore quite stronger than if they would interact like that. And the last thing is the repulsion. Repulsion meaning that those electrons really don't want another electron to be on their place. And this electron exchange is basically exponential. So it's much steeper than the R to the -12, which is normally used in order to make it. And the major reason why we are using in majority of the force fields and majority of molecular mechanics calculations the R to the 12 to the -12 is that it's just a square of the London dispersion that you have to account for. So for one calculation of the London dispersion, you basically get two energies together. So it's easy calculation. The squarification is on computer much quicker than to find out what will be the exponential function, which requires Taylor, and so on. So it's much slower. So several of those interactions are basically making things attached to each other, and that's the induction and dispersion, and some of the Coulombic interactions if you have a different charges. But if you have the same charges, it will move through things apart, and if the repulsion will be taking the molecule, the atoms apart as well. So how we describe those interactions? For instance, the Coulombic interactions we described via the Coulomb law, the charge, and usually, as I've said, we basically take the resp fit, because each molecule is interacting to another molecule via its electrostatic potential, and that's multiple thing. Okay? You can see on this picture that it's interacting quite weirdly, and the electrostatic potential around them is quite complex. So in order to make this calculation, and in order to mimic it as simply as possible, we basically take the surface of this molecule, and then we map what is the electrostatic interaction in those individual grid points. And then that will be our restraint in order to make the individual partial charges on individual atoms. And we will fit partial charges into those individual atoms. So that's how the RESP is done. And the RESP is the typical method to basically prepare the electrostatic interaction, to prepare partial charges for the simulations, for instance, at amper force field. The problem with this method is that you have to calculate the electrostatic potential, usually with some kind of a DFT quantum chemical method, which is expensive and slow. So there are another methods which allows you quicker calculations. And those are usually based on the electronegativity equation methods. And we have an empirical charge calculator for that. Usually what you will find, for instance, in RDKit, it's so-called Gas-Tiger charges. Those charges are electrostatic equalizer, and they can be calculated really quickly. And that's the reason why they are usually dealt with. The problem with Gas-Tiger charges, if you would put them into the simulation, is that they are not as good for how the molecules are interacting to each other as are the RESP charges. Because the RESP charges is basically describing how the molecule would interact with another molecule electrostatically. So it's the closest possibility towards the quantum chemical calculation. There, the Gas-Tiger charges are quicker because they just take the atomic types and fitted against them, but they are quite old as well. So it's not not much precise. In our tool, Atomic Charge Calculator, you can select from approximately 20 different methods for different sets which were found in the literature. And we found out our own method, which is basically calculating, which is dividing the atoms into atomic types. And for each atomic type, we basically have a pre-dealt value. But then from that pre-dealt value, we basically are then taking into account how are the interactions from all another atoms around. And therefore, we are basically doing something similar to the resp charges, and we are fitting towards the set of the resp charges. So this method is giving you the resp-like charges, but in a second, in comparison to the much longer time scale for the quantum chemist. And just now we have started a new server called Alpha Charges, where you can take the structure from AlphaFold and put it there, and it will give you how it looks like. And if you remember from Monday, I was speaking that the transmembrane part of the protein can be quite nicely seen on the top of the structure, yeah, because you have this lily pad effect, and you really can see where the membrane is from the tightness of the structure. You can see that also from the charges. There is part where there is almost no charge, and this is where the membrane is. Right. So it's possible quite quickly to look into the structures to find out what is happening. And you can see that, for instance, this protein is also transmembrane 1. And for small molecules, you can look whether, for instance, to the same group from different molecule and to see how the partial charges changes, and that can be used for calculation of, let's say, pKa and stuff like that. So I've already told about the polarization and induction and how important it is. And now I will tell you that in most force fields, we are not taking it into account because it's slow to calculate it. So what we are using instead is that we are actually putting the induction directly into the force field as it would be permanent one, because we usually take the force field for calculation, for instance, in water phase, and therefore we put how it would look into the water phase directly into the force field. So the induction is usually put also towards the partial charge definitions. Yeah. There are differences, and there can be force fields that are taking into account the polarization and induction explicitly, like Drude charm or amoeba force field, but they are usually much slower because they have to calculate the induction on that specific atom as well. But it might be quite important for chemical reactions. So if you have some kind of a basically, let's say, active site with where some reaction is happening, then usually it's quite different to the common water phase, and therefore it can be calculated with QMMM. And here is just a depiction of how London dispersion can look like. So about Pauli I've already spoken, and this is how the Lennard-Jones is basically made, that you take the dispersion and repulsion together, and you get this minimum well, which is basically the size of the individual atom. The van der Waals or the dispersion bound complexes depend on the sizes and how big the interactions can be. And for instance, the rare gases have only really tiny energy that binds them together. That's usually why they are at the normal temperature gases and not liquids. But if you go towards the bigger system and bigger interaction size, then the interactions can be significantly bigger. And here is one nice simulations from the past, which was done by Pavel Hobza and his colleagues in 2008. And they took the structure of DNA and they basically artificially cut out the dispersion from the force field to see what will happen. And you can see that the pairing of individual pairs is still there because it's bounced electrostatically. And we have these hydrogen bondings to each other, and that's usually the electrostatic multipole interaction. But the interaction in between the individual bases and base pairs is done by the dispersion, and therefore it's compacting the whole structure of the DNA. And I've already said that there is some kind of a hydrogen interaction which is taking and making the interaction between the pairs. And this is usually told as a hydrogen bonding, and it's a one type of a special combination of those interactions I've already described for a specific subset of atoms. And of course, the most important is the hydrogen bond. Hydrogen bond is one of the reasons why, even though water should boil at, let's say, minus 80 degrees, according to this periodic trend, it's, of course, boiling at 100 plus, not minus. It happens in between the system when there is a hydrogen atom attached to a system which is to an atom which is stealing its only electron, and therefore the hydrogen nuclei can interact from another side towards another electronegative atom. Yeah. The effects of that is that the hydrogen is attracted towards the atom Y, which elongates its distance towards the atom X, and it stabilizes the complex. It increases the electrostatic energy, which means that in the infrared spectra, you will get increase in the intensity, and you will get, because the elongation is connected with the lower energy, you will get redshift in that spectra, longer vibrations. Pavel Hobza, one of his part was that they found out that there is so-called improper hydrogen bonding, which is not that much important for drug designing, but it's quite interesting to see it. And in this case, you will have shortening of the hydrogen bond towards the original atom, and it is connected with blue shift and lowering of intensity. So it was not that easy to find those things in the infrared spectra, and the experimentalists before these calculations thought that it's basically an artifact of the measurement. So the artifact was real, it was the type of interaction. So sometimes theoretician can be right, and when the experimentalists are thinking that it's just an artifact of measurement. Another interaction which is important for us is the hydrophobic interaction. The hydrophobic interaction is basically putting hydrophobic compounds, basically non-polar ones, together in a water environment. And it almost see that it's something that is driving them, and it's basic, and it seems that it's basically that they want to be to each other, and that's the driving force. The opposite is true. The water itself, with each other, is binding more strongly. So the water wants more interactions with the water itself because it's more powerful. So it basically excludes the organic molecules out of the water, and by the time basically they are then stick together. Yeah. So it is usually also allowing the waters that would be otherwise bound on the surface of the molecule, which non-polar one, it will release them. So also it's entropically more advantageous to basically cluster non-polar compounds. And since the drugs are usually at least amphiphilic, this nonpolar part usually sticks quite nicely towards the target nonpolar patches as well. So we can use that in order to generate to account for this effect when we are trying to mimic the binding. And the last interactions from these special ones, which is more and more interesting for the drug designing, is an halogen bond. It's to some extent similar to the hydrogen bond because it works similarly in a way that you have the halogen atom bound to some atom that is stealing its electrons, like aromatic ring, for instance. And therefore, on the other side, we are looking at it. So on the other side, looking towards the rest of the world, and is some kind of a positive patch, depending on what type of the halogen it is and how strongly the electrons are taken into the aromatic system. The larger this so-called sigma hole is, and it can make quite strong interactions as well, which are really direct. And that's one thing about the hydrogen bonding itself as well, that it really is direct interaction because it has to look from for the electronegative atom directly in a line from the another one from the atom where the hydrogen is attaching. Yeah. So how strong those interactions are? The covalent ones, speaking in kcal per mole per atom, are usually in a 40 to 160. Carbon-carbon is 100. And Nevím. Hopefully I'm now hearable in online again. Yeah. The another one is pi-pi interaction, which is parallel displays, and that's that's part of the dispersion interaction as well. Then we have sigma-sigma interactions. Again, this is a dispersion thingy, and it's a quite small interaction energy. Then we have the cation p interactions, which is only approximately 2% of the complexes, but it's stronger than those, so it's quite specific usually. Then we have sigma hole bonds, which is those bonds, for instance, the halogen ones, and pi hole bonds, which is really rare. And one type of this interaction is this nitrobenzene interacting with each other. So it's basically electron donating functionality towards the sigma, towards the pi interaction. So we have those interactions, and therefore we can look for those, and we can optimize for those. But we know that those interactions are covered by the energy function. And this energy function is based on the individual distances and individual positions of individual atoms, which makes it a really complex problem because each atom can have some role and has some optimum and unoptimum. And as total, we basically have some kind of a hyperpotential of the potential energy surface. And if we put it down into some kind of a collective variables describing this thing, we can then go from one minima to another. And we are using molecular mechanics optimization algorithms in order to reach those minima, to get the proper complexes, to get the proper poses, and so on. So what we can do is we can do the energy minimization. The energy minimization is giving me to the closest local minima. Then we can do a grid-based method. So we basically can have definition of one torsion, and we can move along and find out some kind of a barrier along that way. That's easy if we have just one torsion. If we have multiple torsions, it's almost impossible because that is so hard to define. If we have plenty of possibilities, then quite oftenly we refrain towards the stochastic methods, which are trying to find out the global minima by random changes or pseudo-random changes, which are then learning. And that's what Monte Carlo or genetic algorithms are doing. Or we can use the advanced molecular dynamics simulations, and therefore we can define molecular dynamics, and we can run the simulations together with some kind of speeding processes like umbrella sampling, metadynamics, and so on. But we have to have something which is defining what we want to speed up the simulations for. So we have to define some kind of a collective variable. For that, we basically are using molecular dynamics simulation. And the molecular dynamics simulation is based on the molecular mechanics, but it adds the dynamics part. So it adds the movement of individual atoms and individual particles. And not only how quickly they are moving by their velocity, but also how this velocity is changing by the acceleration. And we get the acceleration from how strong interactions are acting on that specific atom. So how the force of that interaction, and that's basically taken from the derivation from the potential. So we basically calculate the potential and its derivation for individual atom, and then update how it acts, where it is, and how quickly it is moving. So this is classical mechanics, Newtonian one, nothing quantum or something weird. The only problem is that you cannot go much further because since the atoms are so small, the time scale you can have for each movement has to be small as well. And the smallest time scale, the time scale can be as big as the smallest time scale in the system. And the frequency of movement of the hydrogen atom on the carbon is approximately 1 femtosecond. So we at that time space. The problem is that if you count every femtosecond movement, then in order to get the picosecond, it's 1,000. To get the nanosecond, it's million. And nanosecond is usually not enough, not good enough for the biological system. So you have to go even further for microseconds or even milliseconds. That's a huge amount of steps you need to run the simulations for. So we want to be quicker, and therefore we have to add some tiny tweaks into how to make the longer timescales and how to basically adapt for the different timescales and so on. And also, it starts to be a large amount of data. So if I would have, let's say, 1 million atoms system, like the protein together in membrane and water phase and ligand in it, then I can quite quickly reach 1 million atoms. 1 million atoms and their position and speeds is quite easily for each atom I would need 1 byte. So I would need 1 million bytes, 1 megabyte. Okay, so one snapshot of that simulation would be 1 megabyte. And then I'm speaking that I need to go from one step to gather the dynamics. I would need to calculate multiple snaps. And if I would be counting for individual step and I would just store the same structure after each step, then if I would run microsecond simulation from the femtosecond, it will be 10 to the 9 or 12. I think 10 to the 9. So from it will be 3 steps in the movement of the prefixes. So from the from the mega, which I need for storage of 1 snapshot, giga is 1,000th of them. Tera is 1 million of those snapshots, and peta is 10 to the 9. Yeah. And usually we don't have that much space on our hard drives. So we do the tricks like that we don't store every step, but we store after 1,000 or even 1 million steps. And then we analyze the trajectory afterwards. But in case of drug designing, if we are basically using molecular dynamic simulations in order to just to finalize the drug pose, we usually set up for the picoseconds. Or are you running it for longer? So the difference between molecular mechanics and optimization of molecular mechanics and molecular dynamics, I hope it will be working. Yeah. So it's working. You can see a small movement of the optimization. Do you see it? Not much. So let's start from again. Yeah, the only thing you can see basically is the star at the start that it's moving and then it's just dissolving. And it's not much movement. So the local minima is really quite shallow. In comparison, how it looks like with the molecular dynamic simulation, it's much more joyful, I would say. One thing which is usually not seen from the static structure is this wiggling motion on the benzene ring, forward and backwards, which is quite important if you start to think about the frequencies of possibilities of the interactions of this benzene ring. So it's much more moving, and that's the reason why we are using it in order to optimize towards the global minima, not towards the local one. Molecular dynamics simulations is full of different parameters, because while the original equation seems to be quite simple and easy, we are putting a lot of parameters for individual atom types and individual bonds and so on. And those parameters, thankfully, are transferable. So we are transferring them into so-called force fields. And that's one of the major parameters which we can select when we are selecting how to run the simulation. That we can select the force field. We have to select the force field which has the atomic types for the things which we have. Yeah. So, for instance, if you want to run proteins, then typical one which is used for running the simulation of proteins is either charm or amber force field, but they don't have the atomic types for all the metals. Okay. So if you want to have some force field for small molecules, specifically where there are plenty of weirdness, then you can go towards the MMFF, but this is not good enough for running whole large proteins. So only if you want to do the small molecule optimizations. And from the results which we have from yesterday, from one of our projects, sometimes it's not good enough to work as a start for the QM calculations. As I said, there are the polarizable ones, which are usually running slower, but with the computational power which we have now at the cloud computers and meta centers and large computer centers all around Europe and well, we have the computational power to run those simulations, and sometimes they are giving quite nice results, explaining a specific phenomena. But also we are now moving more towards the larger systems because the cryo-EM is giving us large system, and to run the large simulation of multiple proteins together in some virtual cell, it would be impossible to run that out atomistically. So we use some coarse graining to run that. I've already said that another important parameter is time step, and for the optimization, when the structure is not yet optimal, I suggest to use really small time step. When the simulation is in the productive state, then you can move towards 2 femtoseconds quite easily. And for instance, in GROMACS, it's possible to use the virtual sites to take care about those tiny hydrogens and to speed up the simulation to 5 femtoseconds. And if you are using, for instance, Martini, there are possibilities like 20 femtoseconds, and if you are not using cholesterol, 40 femtoseconds even. Yeah. So it's possible to go quicker with those simulations, not only by having less amount of the particles in coarse grain, but also having a larger time step and therefore increasing the speed. In our simulations, we need to set up also a temperature and pressure usually. And for temperature, it's important to use the thermostat that is taking care about the temperature. And there used to be for a long time the most used one Berka, but it was shown that the Berka unfortunately is giving non-canonical an ensemble at the end. So it's necessary to use its new version, which is called Puri scale, where you add some stuff in order to reach again the canonization. And pressure barostats are usually for the pressure we use the Berka and so on. So how the molecular dynamic simulations can be used? Okay. They can be used for taking care of the flexibility of the receptor. So it basically can accommodate for the ligand. For instance, in one of our studies, we ran the molecule going from the active site via the channel towards the surrounding. And we found out that the flexibility, which was shown in the molecular dynamic simulation about how the molecules interacted, at the end, the molecule was moving like a moving bubble within the protein structure. So it enlarged quite a bit the tunnel in comparison to what we would see, for instance, with mole channel analysis. It gives us the optimization of structure, and that's one of the reasons why the AlphaFold structure, after it's built, it's just run through the optimization by AlphaFold, via Amber force field. It includes the solvent effect, and it can confirm the poses, and we can even calculate better binding energies. And that's for another part. So take-home message from this first lecture, which I unfortunately took longer than I expected. The molecular mechanics is the approximation of molecular interactions. So we use that in order to understand how the molecules interact to each other. Usually what we have in all of those parameters, there are error cancellation everywhere. So we basically are using the harmonic approximation, even though we know that in some places it's not perfect, but for where we are, it usually works well. So we are trying to be on the safe side there, but there is error cancellation. The non-covalent interaction are strong in their weakness because of their numbers. And we are basically moving along some kind of a potential energy surface, and the molecular dynamic simulations can give us that. So, are there any questions for this presentation? If not, I would be immediately going towards another one. Okay. And another one is the major topic of today, and that's molecule docking. What we are trying to achieve with molecule docking? We are trying to find the best fit of ligand to receptor. Similarly, as Calvin is fitted to the hops in this picture. But in a protein sense, we have a protein, we have its binding site, we have a ligand, and we want to generate a complex, which is called pose. And we want to get some kind of knowledge about the energy of that pose. So we want the binding energy, but quite often we don't get binding energy per se, which would be really precise, but we get some kind of a score that is approximation of it. The binding pose is usually how the molecule looks like. And this is the results of redocking of the today's tutorial. So it can be quite similar to what was actually in the crystal structure, but there can be differences, like the position of this fluorine atom. And all of this, how it will look like at the end, is driven by molecular interactions. In order to describe those bindings in the experiment, it's usually measured in multiple weird values like IC50s. But we can take those IC50s usually as some kind of by some kind of approximation of inhibition constant usually. And from the constant, we get the binding energy, and therefore that's the equation which we are trying to compare with. So we are using the calculated binding energy by accounting for the interactions, and we are comparing to the experimental one. The IC50 by itself is somehow similar to Ki, to the inhibition constant, but it's also depending on the system. So it's depending on how much concentration of the substrate was used and how big the Michaelis-Menten constant of the enzyme was. Yeah. So it's the approximation of IC50 towards the Ki as they would be equal is not precise, but is often used because it's much more easy to measure IC50 in the experiment than to measure to get the Ki from the experiment, because it's really usually it's hard to get these two things properly. What we often see, and actually that was one of the things which the Campbell was showing as well, that they usually take these values and they logarithmize, and at the end they make them logarithmic again. Yeah. And that's usually how it's shown. So it's usually shown as the negative decadic logarithm. And in this way, it's going to give the proper normal numbers. And depending on that, you basically get the idea about how good binder it is by just looking for the concentrations of these IC50s. If it's binding with the picomolar affinity, then it's excellent binder. Usually this is not what is happening for small molecules. It can be for the antibodies. Yeah. Because one of the reasons why it is for the antibodies more often than for small molecules is that we get the larger interaction surface will give you stronger binding. And this stronger binding will move towards the that you would need less amount of the compound to actually bind. Usually what we get in a for small molecules is somewhere in between nanomolar and micromolar range. So this is usually what we usually see in the docking sessions. And the docking software is basically taking these energies and trying to find out the best ones. And for that, he needs to have some kind of a scoring function. And it's not necessary that the same scoring function is used for everything. And it can be, it's just some scoring function which is cheaper, can be used for a first search. And then for a final refinement, you can use a different one that would be more precise. Or you can, for instance, use the docking to find the poses with, for instance, Autodock Vina, and then use molecular dynamic simulations to basically get more precise delta Gs. I've already said Autodock Vina, and there are several types of different scoring functions you can find. There are several based on the force fields. So, for instance, Autodock was based on the Amber force field and tuned into a scoring function from that, the original Autodock. Then, when you have something with the force field, you get the error cancellation similarly as in the force field. So Martin Lepšík, who already left, they are in his group and in the group of Pavel Hobza, they are trying to go for the quantum mechanical based scoring function using semi-empirical QM like PM6 and its versions. and they can achieve much better description of the system because their scoring function is better descriptive of the system. But it has, of course, a limitation of the times that the calculation is more expensive. Then you can have an empirical one, which is parameterized against experimental binding affinities, so KDs and IC50s. And it can contain an arbitrary chemical terms like the number of hydrogen bond donors, hydrogen bond acceptors, hydrophobic contacts, metal ion interactions, and so on. And these ones are quite successful, but only for similar compounds. If you use them on something else, they were not trained on, they usually fail. Instead of using the experimental binding affinities, which also has some kind of an experimental noise, I would say, you can use the protein ligand complexes to basically tune up the binding according to reproduce the protein ligand complexes. And there is this hypothesis that the both which is in the crystal structure will be more strongly bound than any other, and therefore, if you would have the scoring function that would prefer that would be quite a good estimator of the binding energy. And there are stuff like that, and one of them is actually one autodogina. So the force field scaling functions are counting the physical interaction terms similarly as I've shown you an hour ago with the molecular modeling. But in case of the docking, we are using some tricks not to count for everything and to speed up the calculation. The first trick is we don't calculate those four. We don't calculate bonds because we said that the bond is of a specific length, depending, that is typical for that type of the interaction. So that's easy. We don't calculate the bond movement. The same thing happens for the angles. We just tabulate them. For the dihedrals, you will see. And then we are calculating only for the interactions of the intermolecular terms. And the dihedrals, we usually count only within some kind of degrees, not specific. And then we do another speed up, and another speed up is using a grid. And that basically molecular dynamic simulations or molecular mechanics is calculating the interactions between every atom within some kind of a sphere. It's counted all together, each atom to each atom, in order to get the most precise force that is acting on that specific atom. But we don't want that because we basically usually in docking scheme, we have one structure of the protein, which is the same for all of the ligands which we are trying. Okay, we can have multiple different versions of the structure, but usually the most typical version is that we have one structure of the protein and we dock ligands into it. And the only thing which are changing is the ligands. So it's easier to first count this grid into the protein. And on the grid, we basically count what is the interaction energy at that specific point for the specific atom type, whether that would be on that spot. And then when we put the molecules on that, we basically have the interaction energy much more quickly because we don't calculate the real distances of that specific atom to any other atom within the protein. But we are looking for what is the closest grid point, and we take this energy. And summation and the finding within the grid is much quicker algorithm than to calculate the distance, square it, and moving like that. So that's the major reason why to use the grid in order to time saver and to use the table search instead of full energy evaluation. But of course, there can be problems. And one of the problems is that we don't calculate the repulsion right. As I've said, the repulsion is exponential by nature. But we usually use R to the 12 in the Lennard-Jones potential, which means that if you have a pocket which is quite close, which can happen to in the kinases, for instance, then the molecule will not fit because the atoms will be a little bit artificially bigger. And since in the molecular dynamic simulation, it wouldn't be a big problem because you would move that 0.0 angstrom apart, seemingly nothing would change, but now the molecule will fit. But in docking, especially rigid one, the protein is not moving at all. You get those grids. And therefore, you can quite quickly reach toward the repulsive part. So in order to overcome that, we developed a dock 6.6 with the exponential repulsion. And this docking was slower, but only a tiny bit. But we were able to reach the closer to the crystal position with this redocking. And we showed that it's only happening, and this is only happening when you have the really narrow tunnels or narrow binding sites that normally in molecular dynamic simulation, they would breathe, and therefore they would let the ligand in molecular dynamic simulation. But in the docking, you might not find them. One possibility how you could find them would be to use the QM-based scoring function, like the one I'm showing here. But now it's much more complex, I would say. And it was shown on Martin Lepšík's poster. So I hope you've seen it all. Then the empirical scoring functions. The empirical scoring functions basically are trying to decompose the energy into chemical terms so they can be afterwards used to lead up further development of the drug for a chemist. And therefore, they are the hydrogen bonding, pi-pi stacking, and so on. And you basically use some linear term. This is one of those cases. This is the BEM scoring function defined binding energy by some kind of a parameter, which is just fitted. And then you have a fitted parameter together with the number of hydrogen bonds, a number of ionic interactions, size of the lipophilic part, and the number of rotational bonds. That's it. So it's relatively easy description. It has its chemical meaning, so it's possible to basically use that. And the only problem is that it's usually tested on some type of the protein ligand combination, and you have to use it for that type of a combination. And it cannot be used anywhere else. The knowledge-based function, as I said, is using the statistical mechanics. So it basically counts what are the preferential bindings toward, let's say, typical position of the ligand in a protein, and to those most often typed poses, it's stronger energy. So it basically accounts for how often this motif happens, then it gets its energy according to that. So those were all different types of the scoring functions. Nowadays, of course, those scoring functions are tuned by machine learning and by steps like that. But in general, originally they came out like this. And I'll come to that later on when I'll be speaking about the quality of the scoring functions. But now I have to step a little bit further to speak about how to prepare the docking procedure. Because the docking procedure has to be prepared similarly as the molecular dynamic simulations. There are several parameters that have to be accounted for. And we have to speak first about the receptor, because the receptor itself has to be selected to be representative for what we found, what we want to achieve. We had to find the relevant one. And we have to prepare it for the docking. Then we have to do the same thing for the ligands. And I'll show you that sometimes it's not that easy. And there are several other things like what to do with water and what to do with flexibility. So what to do with the receptor? For the receptor, we have to first find where actually we want our drug to bind. So we have to identify the binding spot. Then we have to find a good structure. And as I've said in AlphaFold lecture, nowadays we can even use the AlphaFold to do that. But we have to be careful, and we have to validate whether the results are making sense in most effective way via the experiment, of course. But we have to be careful about one thing as well, and that's that, for instance, we have two different structures of the protein. This one is apo, this one is holo. If we are looking for the optimized structure, then the optimized structure for the apo version, therefore without ligand, will be this one. And if we add the ligand into it, we can move only that. But if we took it into the holo conformation, then the binding of the ligand will be much more official. And that's the reason why this holo structure is actually present, because in combination with the ligand, this is at the end the global minimum. So we have to look for the structures that would look like the holo ones, usually, because those are the structures which are accommodating some kind of a ligand, so they might accommodate our ligand as well. But of course, individual type of the structure, and that's where the annotation comes in. We have to know what the structure is good for. For instance, if I would have the GPCR receptor, there can be two types of the ligands bound to that: the antagonists and agonists. And the structure of the protein will be different depending on whether it is in agonistic state or the antagonistic, inhibited one. So if I want antagonist, if I want inhibitor, then I need to select the structure which is antagonistic. But that's necessary to know before we start docking, because afterwards we will be automatically selecting for the agonist one if we would select the agonistic structure. So that's the reason why it's quite often quite important to look for what structure we are actually selecting. And this is our experience example. This is the docking which I've done together with the dean of this faculty in the past. And this is the sodium-potassium ion pump. And we were trying to where the individual type of the fluorescent probes, which are used to analyze this protein experimentally, where are those probes actually binding towards the protein? Because they had some measurements that did not fit into the original idea that there is just one site for the binding. So we put it into the docking, and there are two ways. The one way is this is the binding, the domain which is binding the ATP, and this is the ion channel itself. And when we docked into the whole structure, we found out that basically one place where the drugs is binding is towards the membrane. membrane protein interface, but we haven't seen any any structure, any ligand docking to the towards the ATP binding domain. So we knew from the experiment that this is not true. So we knew that there is actually one spot that it's binding towards the membrane part, and we were trying to find out the another. So we took only this domain, tried to look for the where it will bind. And this domain has two different conformations, ATP bound and free. And when we docked into the free one, it was a mess, complete mess. We weren't able to see anything, and those energies were terrible. But when we selected the structure which was like the ATP bound, we immediately got quite nice cluster of the structures around here. And we were able to identify that it actually acts there, and it explained the experiments that the probe is actually interfering with the ATP action of the protein. So it can help, but only this only shows that it really depends a lot on the conformation of the protein. What will your results be? So wrong selection of the protein at the beginning means wrong results at the end. Think about that at the challenge in Friday. Then another thing which is important to notice, and that's the protein conformations of the individual amino acids. Because usually when we do the docking, in order to make it quick, we use one structure which is completely rigid. But of course, that's not happening. Yeah. The molecule, when it's interacting with the protein, it is affecting the structure of the protein, at least close by. And that's not accounted for. And that's the reason why I actually am saying that you usually should use the holo structure, because that structure is already prepared to be binding something. Yeah. And thankfully, for the docking towards the alpha fold, this is what the alpha fold structure looks like. The structures where the ligands are usually bound in 80% of chances. But sometimes you can have some kind of a floppy side chain that is moving in and out. So if there is several structures of the active site, it's usually quite useful to compare them all together and to see whether all amino acids are sitting at the same place. And sometimes you will find one amino acid which is moving along, and it's possible to define this one amino acid as a flexible one in a docking. So then you just add it into the docking scale, and it will allow the movement of these structures. Sometimes the another thing you have to think about is that the interaction energy will be depending on the size of the molecule. This is our docking into the histamine 1 receptor, where we had these compounds found in Portugal and analyzed in St. Petersburg for their anti-allergic properties. And what they knew was that the package of monomers and dimers is actually making those, but they did not know which of those molecules is causing the effect. And we found out that when we use smaller molecule, then it bound quite nicely into the active site of this G protein couplet receptor. So it was having an effect. But if I would be blindly going after the best energy, as we are, if we are comparing the large data sets, then this one would win. Because since the molecules were twice as big, their energy was bigger. But it was not bigger twice, it was bigger like 1.2. And it's much more messy. So if I would be blindly following the best energy and not looking to the poses, I would say, okay, these are binding stronger, therefore that's it. But we have to be careful about the comparisons, because this small molecule is binding actively to the specific place where it can have the effect. So at the end, it's the smaller ones that are having the effect, not the bigger ones. And there are another problems with the protein structures as well, which is the receptor itself has the amino acids that can be changed. And one of those typical problems is histidine, because histidine has the pK of 6, and therefore it can has the hydrogen here or here on both sides in a protein. And you have to look into it if it's close by to the active site and to find out what is happening. And again, it can change a lot the result. Ligand preparation. It's usually quite good to look what the ligands are and how, where they can be changed. Because oftenly you can get from the experimentalists that there is C2, so there is a double bond between the carbons, and this is a rigid bond, and therefore it won't move in a docking setting, and you have to prepare it beforehand. So you have to only think about the conformers and rotamers, and all the previous ones, like cis-trans isomers, enantiomers, and structural isomers, the docking will not dealt with. You have to deal with that beforehand. And with this, the ligand conformation is usually counted by the rotation by a set of degrees, and it can have a problem. So, for instance, this is quercetin, and this quercetin has this one rotatable bond. So when we've looked into the crystal structures, we found out that those rotatable bonds are usually around 180 degrees or 360. So it's just plainly one or this rotation. When we added the calculation, there is plainly seeable 2 minimas. But when we looked into the publications, you can see quite easily that this is 90 degrees. This is 90 degrees. So it's completely wrong. And the major reason why they wrong is that this bond, by the definition of the program, is single. And therefore, the docking programs usually take it as a fully rotatable. And from the sterical clashes, it will end in 90 degrees. And therefore, the molecule will be quite different at the end. And this is the example from our past as well, where we found this type of molecule, biphenyl, bound to the purine moiety. And when we did not think about that, we got completely rubbish results all the time, because we get these 90 degrees. But when we fixed that, we immediately got a right structure, and we found, and this is actually interacting with with these histidine. So we had to think about the histidine as well in this docking procedure. And when we thought about that, then the results made sense, and they were actually following the experimental trends. But we found that automatically, just by blindly trying, that we wouldn't survive. And here is another problem, and that's when experimentalists set us some structures, and they send it via, they have it in their ChemDraw, and it's steroid structure, so they all the time they knew that it looks like that, and they doesn't care more. When we we asked them, okay, can you send us an SDF file, a structure data file? So they said, yeah, here it is. We opened it in Pymol and it looked like this. Quite weird bondings, right? When you look at it from the side, you immediately realize it's actually 2D structure, not 3D. Okay, so we run the 3D optimization. You get the structure like that. But in my original past, I was organic chemist at the IOCB, and I was making the brassinosteroid compounds. So I knew that this is a wrong one. So when I thought about the structure of the testosterone and optimize it, this is how the structure should look like. And again, if I would blindly take the experimentalist's data and blindly applied it, it was going to the mess. So there are plenty of open resources you can use to run docking, and you can use them for multiple things, like to find some targets, to run the virtual screening, to make the rationalization, what to do next in an optimization of the drug molecule, to try to use the drug for a new target in drug repurposation, and look for the prediction of adverse drug reactions and so on. And you can add it together with other methods, like the artificial intelligence or molecular dynamic simulations or some ligand-based approaches. But I'm running out of time, so I'll just quickly skip to the next slide about the quality control. And there we have to think a lot about that we need to validate what is going from the docking. The first and easiest part, which we will be doing today as well, is to redock back the molecule to the crystal structure. And if that fails, something is really fishy, and we need to first find out what is wrong, because any new molecule will be even worse than the original one. Then the correlation towards the experimental values needs to be somehow decent in order to that the things are working. But there is quite a lot of noise in the experimental data, especially if you are combining the data from multiple laboratories, like if you take the data from camp, for instance, because there are data from different labs moving a little bit different protocols and so on, and therefore there are differences in individual datasets. There are datasets taken from the validation, so you can use those, but normally you wouldn't see much by using those, because this is basically a benchmark for the development of new scoring function or new programs, but it won't help you in that specific project you are currently working on, because for that you need to have some kind of validation data on your own. Yeah. And in the virtual screening, we basically are looking for the enrichment factor and ROC curves. This is how ROC curve works. It gives you here on the x-axis, you plot the false positives and therefore the negative ones, and here the true positives. And you are trying to achieve as high here and as small as there, and you count for the area under the curve. So here are some types of this. So for instance, this is the ideal one. So first you found everything which is positive, and then later on all negatives. But in reality, it will work like usually something like that or that. Yeah? So you will see only a small enrichment of the really very positive counts. And if I remember correctly, that's basically what you will be doing in the ligand challenge. You will be trying to enrich and to have your ROC curve as close to 1 as possible. So the last point is the comparison of multiple different scoring functions. And there was similarly as CASP, there was a comparative assessment of scoring functions competition, which was run in a SU lab in PDB bind. And it was the last version of it ran in 2016. and it compared these scoring functions based on the scoring power, so the correlation to the experimental binding data, ranking power, so ranking known ligands against the to precise poses, docking power to identify binding pose which is native, and screening, so to find out the true binders from the decubus. And well, what's happening? This is really weird. So the best one was random forest descriptor based on the results from VINA, but the VINA is relatively close by. It should be a little bit higher, but it's decent one. For ranking power, again, based on the VINA, you can apply the machine learning on that to get a little bit better than the rest. But you can see that the correlation coefficient above 0.5 is typical in the field. For the docking power, the VINA is actually the best. So to identify native ligand binding pose, it's really good to do so. And for the screening, to basically find the true binders, again, machine learning based VINA on VINA, but the VINA is not that far off. So that's the major reason why the whole world is using VINA, because it's for free, it's open for everybody, and it's giving decent results. So, take-home message. Molecule docking is useful when you are trying to find how the molecules bind and which molecules will bind towards some target. But it has to be taken with a grain of salt always. You have to validate, because it's a computational method which is really approximative. So you need to really think about it. And there are multiple troubles. You have to be careful about when you are preparing your ligands, when you are preparing a receptor, and when you are scoring. With that, I'm finished. And I'm sorry that I've taken 7 minutes from the coffee break. But still, do you have any questions? If not, then it's coffee break.
So 1, 2, 3, 4, 5. Don't really know if is it better like this? Hello, hello.
Well, it's on. So now I'm just checking with the people who are
Okay, because
whether they are hearing.
Yeah, because my voice is not so strong. I'm sorry for this, but yeah, if it is fine. Trying to say something. Do you hear me?
Say something whether I don't get any.
А потом перейдем этот счет.
Хорошо, просто подписал, да? Куда? Здесь?
Да.
Подпись или полностью?
Можно фамилию, фамилию и подпись. Подпись вам должна быть самая основная.
Спасибо.
So we can start this presentation. It's already 11 o'clock. So this presentation will be made by Semen Yesylevskyy, who is from ISTP and formerly from Ukraine. So he will present topic also related to microdynamics. I hope we will know something really new and great.
Yeah, thank you for introduction, and I want to thank the organizers for giving me opportunity to give this talk. It's not a lecture, it's more like a talk. And the topic is the druggability of the lipid membranes and insights from MD simulations, but the scope would be a little bit broader than this, because I want to say a bit more about the applicability of MD simulations to the membranes and the implications to drug discovery in general. So we will start from looking at what is druggable now in the pharmaceutical industry. And if we will make some statistics, we will see that over 95% of all drugs are designed for protein targets. And in the recent years, some drugs are also designed for the nucleic acids, for DNA and RNA, which is mostly small interferon RNAs, antisense RNAs, and different modalities of gene therapy. But you will never find membranes, at least. So the membranes are not considered as drug targets usually, and there are no approved drugs for the membrane targets. So what is special about the membranes which makes them undruggable? So first of all, there is no structure. If you look at the membrane, you see the liquid crystal, there is no defined structure like in proteins, and the composition is not predefined as well. For example, membrane composition is not defined by the genes, it's regulated dynamically. There's no change involved in space and time, even in the same cell type, for example. And in different tissues and cell types, the differences between lipid compositions are relatively small. And the different organelles inside the cell also have different compositions that complicates the matters even more. What is crucial about the membrane properties is lipid composition and symmetry of monolayers and the membrane curvature, and all these have to be taken into account if you want to think about the membrane as about the druggable entity. What kind of drug we can imagine to be selective or acting somehow on the membranes? Such drugs are known, but they are not designed especially for the membranes. They are called membranotropic drugs or membranotropic agents. And they are often found by accident. So this is accidental property considered as kind of side effect of the drug discovery. So oops, our drug interacts with the membrane. The definition of membranotropicity is actually accumulation in the membrane. It's very simple. If it accumulates inside, then it's membranotropic. And this, in this sense, the membrane is often considered as kind of unfortunate barrier for the drug delivery. And the membranotropism of the drug may help to overcome this barrier to some extent. But as far as I know, almost nobody is looking for this. There are few studies of membranotropic effects of the drugs, but not so many. You can actually use fingers of one hand to list all of them. And the big problem is there's no structural similarity among the membranotropic drugs. You can only tell that all of them are amphiphilic, and that's all. So here you can actually see almost all the known drugs which were studied and which are experimentally verified to be membranotropic. Maybe there are 2 or 3 more than these, but this is pretty much. And as you can see, there is no structural similarity. The molecules are very different. All of them are amphiphilic in some sense. But there is some tendency in terms of the classes of the drugs. For example, there are several molecules which are analgesic, several anesthetics, and quite a lot antipsychotic drugs. And all of these 3 classes are actually acting either to the membrane receptors or to the neurotransmission and the release of the neurotransmitters in the brain. So they can act on the level of the membrane, and it's quite natural that they interact with the membrane. But at the same time, we have, for example, anti-cancer drugs, several classes of them. Here you can see doxorubicin, for example, but this is true for whatever rubicin, there are a lot of them. All these compounds are quite complex in comparison to others, which you can see here, but all of them are kind of amphiphilic. And there is one drug which is lipid lowering. It's somehow related to the lipids, but not to the sense which you want to see. It's not about the membrane lipid, it's about the lipid metabolism, but this drug is also membranotropic. And on the right, you can see remdesivir, which is antiviral, and ticagrelor, which is anti-platelet agent. And these 2 drugs were not known to be membranotropic. And in our works, we actually proved that they are membranotropic in the last 2-3 years. So, if we will imagine that we want to design the drug which is membranotropic and we want to target the membrane, how it can work? So how we can imagine the modality of this drug? So first of all, we can imagine direct interaction with the plasma membrane and direct action on the membrane. So we can change physical properties of the membrane like ordering, fluidity, phase separation. We can also modulate passive diffusion of other compounds by changing these properties. Second modality, we can indirect act on the membrane proteins. So we can change the microenvironment for the membrane proteins. For example, many raft-like proteins don't like to be in the liquid fluid phase. So if you will enforce this phase, it will disrupt interaction with the receptors in a way. We can inhibit multimerization of the membrane proteins, which is especially important for receptors and ionic channels. We can try to interfere with the membrane-exposed active sites, which is true, for example, for rotary apophases, or we can block the allosteric lipid binding sites. And the last one is a dual action. So we can imagine the drug which changes the microenvironment for its own protein receptor. It sounds like something crazy, but I will show later that it's possible. Next step, each drugs have to be selected. So is it possible to be selected for the level of the lipids? Well, the answer is yes and no. As I said, the differences in lipid composition are quite small between the cells. But for example, in cancer cells, we know that the lipid asymmetry between the monomers is disrupted. So in cancer cells, phosphatidylserine is exposed to the outer monolayer of the membrane, and the overall distribution is scrambled. So for example, PC and PE appears on both sides of the membrane equally, which is not the case in the normal cells. And also there are some differences in the membrane curvature. For example, cancer membranes could be either less or more curved than their counterparts from the normal cells. The next class of the membranes which we may try to target are viral membranes. And here we see the difference because they usually originate from the endoplasmatic reticulum. So they are distinct from the plasma membranes of the cells because they are low in sphingomyelin, ceramides, and cholesterol, and there is no asymmetry. And also in terms of curvature, viral membranes are usually positively covered uniformly because you have kind of spherical particle, which is not the case for the plasma membrane. And the last case are bacterial membranes, which often contain very exotic lipids, especially if we are speaking about gram-positive bacteria. This was the kind of boring part. Now we will look how we can apply MD simulations to find some membranotropic drugs and to prove that we actually can work on the level of the membrane and prove that the membrane is druggable. So we will speak mostly about realistic composition, asymmetry, and curvature of the membrane. And let's start from the composition. Actually, it's nothing to say because the problem of lipid composition currently considered to be solved for MD simulations, because MD force fields for the lipids are considered done mostly. Major lipids are ready. Many non-standard lipids could be built from the building blocks of other lipids. And of course, there is a tool like charm GUI, which allow you to create any membrane composition you want really fast. And like 10 years ago, the job which could be done now in 1 day took like 2 months. So it's really invaluable tool. But there are some issues, of course. First of all, bacterial lipids. They're too crazy to be built from existing building blocks. So if you're working with bacterial membranes, you end up with a problem of parameterizing the bacterial lipids. After that, there is a problem of heterogeneity of the fatty acids. For example, in a real cell, you have about 25 types of phosphatidylcholine itself. So do you need all of them or not? If you want to simulate all of them, you would not have enough lipids in the system to represent at least one lipid of each type, because there are so many of them, and you're working with like several hundreds of lipids only. But these are kind of minor problems, and in general, it's doable, and you can simulate any lipid composition. The next thing is asymmetry. So we know pretty confident now that almost all eukaryotic plasma membranes are asymmetric, and also many bacterial membranes are asymmetric. If we are speaking about eukaryotic membranes, here you can see the diagram for the red blood cells. And it's evident that actually outer monolayer is enriched with the neutral lipids and glycolipids, and almost all sphingomyelin and ceramides are actually outside. But inside, you have almost all anionic lipids and almost all ethanolamic lipids. This figure is pretty much the same for all cell types with some changes. And this asymmetry is created by fluidizases and scramblazes in energy-dependent manner. So the cell is paying very high cost in terms of energy to maintain this asymmetry. Which problems do we have here? First of all, experiments are quite complex. You can do this easily on the red blood cells, but not so easy on the other cell types. In terms of cholesterol, it's extremely hard to measure experimentally, and nowadays we only know some hints about cholesterol distribution. It's almost impossible to get. It's also hard to measure dynamic aspects like lateral diffusion and lead walk transitions, because again, the resolution of experimental technique is not enough for this usually. And there is no way to get the atomic details. So we need to use these simulations to overcome this. If you want to simulate the real lipid asymmetry, we immediately get into the problem, because we have asymmetric system and the area per lipids for different lipid types is different. So each lipid takes certain area on the monolayer, but it's not equal. And if the monolayers are asymmetric, we will get with a system like this. If we put 64 lipids in each monolayer, one of them would be larger than the other, but we have to pack it with the same box. So we need somehow to compensate and put more to the monolayer with a small area. And this is partially resolved in the tools like CharmGUI. What they do, they maintain the library of pure bilayers from different lipid types. And when they construct the system, they're mixing and matching the lipids and trying to put as much as possible to fill the box. It works, but not always. So the equilibrium for a single lipid type is not the same as equilibrium for the mixture. So sometimes you have some artifacts in different areas. And of course, it fails in the non-standard conditions. But this is the best what we have now, and most of the time it works. Here is a case study. So does it really matter? The answer is yes, it is. So what we have here, we have the comparison of the normal plasma membrane, which is modeled about red blood cells, but it doesn't matter because all the membranes are pretty much the same. And here you can see the lipid composition of this membrane, which is for the normal asymmetric case of normal cells. Numbers here are different studies which are cited in the text of this paper. And actually, this is kind of distribution which is found experimentally in these papers. They're mostly consistent with each other, and you can see that phosphatidyl-halide sphingomyelin is mostly outside, PS&P is mostly inside. Now, if you will work with the cancer, in the cancer cells, the distribution is like this. There are only two papers which can be compared, but it's quite evident that this asymmetric distribution is pretty much scrambled. So everything is equalized, and the distribution is almost identical outside and inside. So these are two model systems, normal membrane and cancer membrane. As you can see, here it's kind of bicell. So it's not the bilayer which spans the simulation box, it's a bicell. And the reason for this, if you do this, you are free from this problem of the area. So the lipids could redistribute freely and actually compensate for the difference of the area, but this is not the biggest point here. So actually, what we get something like this. First, if we try to look at the properties of the membrane, for example, the distance between the lipid head groups, you immediately see that if you change from the normal membrane to the cancer membranes, there is some difference. But if you change the cholesterol content, there is a huge difference. So cholesterol is much more important for its properties and the asymmetry of the monolayers. The same is true for the distribution of the tails density and for cholesterol density. So because as you can see, it's a huge difference between 15% of cholesterol and 30% of cholesterol. Then if you look at the ordering of the lipid tails, this is the plots of the lipid order. Depending on the carbon number in the tail, you can see that again, if you go from the normal to cancer with the same cholesterol content, there is some difference, but not that much. But if you go for the lower cholesterol contents, all the curves are dramatically different. So the loss of asymmetry changes these membrane properties, but not dramatically. Cholesterol contents matters much more. So the question is it enough to influence the membrane permeability to change the asymmetry itself? So here we computed the PMF, the potential of mean force of transferring the drugs from outside to inside of all these membranes. And the drug here is cisplatin, so very well known anti-cancer agent, which is widely used and abused, I would say. And here you can see the permeabilities, coefficients for pure DOTC lipids for normal asymmetric membrane without cholesterol, normal membrane with some cholesterol, and normal cancer membranes with 33% of cholesterol, which is kind of normal. And as you can see, if we will compare normal cancer membranes, the permeability difference by an order of magnitude. But if we look at the PMS, red and magenta curves are pretty much the same. There is some difference, and this is enough to get an order of magnitude here. So yes, asymmetry matters. Despite quite minor apparent changes, you are getting 10 times differences. Okay, the next story is the membrane curvature, and this is the most difficult and the most probably interesting part. So here we need first to find with a bend the membrane it appears. We need to maintain the curvature in the simulation somehow, and we want to produce the properties of the permeability. First of all, if you speak about realistic curvature, almost all cell membranes are curved. If you will look here, any cell organelle which you can imagine actually contain curved membranes, and sometimes the curvature is really high, like in the endoplasmatic reticulum or in Golgi. The reasons for this bending is also quite well known. First of all, there are different membrane proteins which cause the curvature. Then there is a cytoskeleton which actually also causes curvature in cilia and extracellular extrusions. And there is also intrinsic curvature, which is dependent on the shape of the lipid molecules. So for example, if you have the lipid with equal volumes of the head group and the tails, there is no curvature. If it is cone-shaped, you can have either positive or negative curvature. That's great. How can we simulate this? I will skip this because it's not so important right now. So we have the same issue, but with the membrane tension. Again, we have to pack the system into the simulation box, but due to the bending, the volumes and the areas of the monolayers become very different, and we have some tension in both monolayers, and we don't want this because in the cell it's not the case. There are several approaches how to simulate curved membranes. So first of all, you can start with a large piece of membrane in the periodic box and just run it as it is and hope for spontaneous undulations. Then you can do what is called membrane buckling. So you take the flat membrane in the box and you squeeze the box. So the membrane, due to this squeezing, become of this shape, which is quite nicely looking, but not so easy to analyze. Then you can apply some proteins which are responsible for bending the membranes in the cell, and you can simulate these like bar domains, which are causing the curvature. And finally, you can scaffold the membrane itself. So you can apply some dummy particles which will maintain the shape of the membrane, or you can enforce the curvature by external forces. Each of these techniques have downsides and advantages. If we are speaking about spontaneous undulations, there is no setup required. You're just running the simulations as usually. But it requires a large system and long simulation times. It's unpredictable, and it's almost impossible to sample large curvature because you have to wait until it appears spontaneous. If you are doing membrane buckling, it's also quite easy to set up. It allows applying mechanical forces and estimating mechanical properties if you need this. But the curvature is induced by external compression. This is not always what you want. You are getting strained elastic bending of the membrane, which is not always what you want. And the curvature is not uniform. Here you can think that this is sine wave. It's not. It's a convex curve which is called Euler elastica, which is crazy in terms of mass. So it's quite hard to analyze. If you're speaking about protein-induced bending, it mimics the natural system, which is good, but you don't always have proteins in the system. And the bending is not always protein-dependent, so it's quite limited. Finally, if we are speaking about enforcing the curvature by external forces, it's the best way to do it from the physical point of view, because you can maintain the curvature without global strain and without proteins. It's also uniform, so it's easy to analyze, but it's methodologically complex. For example, it almost always requires either Dumi particles or modification of the code of your MD engine, which is not always possible and easy. Now, I'll go a little bit deeper in this. So, for example, if you want to maintain the curvature by applying the Dumi particles, it works pretty much like this. You're applying two balls of Dumi particles, which interact only with the lipid tails here. And all the rest in the system don't see them. In MD, you can do this because you're a god, you are playing these interactions. So they are only defining the interaction between the Dumi particles and the center of the bilayer with the carbon tails. And head and water doesn't see them, and you can maintain any shape you want. It's also fixed in space, so it's easy to compute the PMFs in this configuration, but you have these unphysical Dumi interactions, which is not always good. Another thing, you can enforce the curvature by radial pulling, so it's shown schematically here. So you're computing the midline of the membrane, you are pulling the midline in terms of some kind of cylindrical geometry. And in this case, you have no Dumi particles. You can generalize the center of mass pooling, which is already present in MD giants, to do this. It's also system agnostic and it's parameter free, which is always nice. So you can change the force fields, do whatever you want. But it requires modification of the MD giant. And also becomes much less efficient without this modification. Okay, so what we get in the case here, this is a work where we apply these Dumi particles to study the permeability of the membrane and the same composition. Again, this is a composition of the human red blood cells, but now depending on the curvature. So this is a composition of the membrane, so it's pretty much sphingomyelin, PCP, PS, and cholesterol, and it's asymmetric. And here you can see from the covering of the lipid that it's really quite asymmetric. This is a flat membrane. And here the curvature actually matters if it is positive or negative curvature here the system is asymmetric. So if you bend in the opposite directions, the topology is different. So you have to simulate three of them. And again, if we will look at the properties of the membrane, again, the distance between the head groups changes a lot if you go from the flat to concave or convex surface. The distribution of the tail changes, the distribution of cholesterol also changes, but the most important, what goes on with the lipid ordering, because if you will look at the ordering of the lipid chains, you see dramatic difference if you go from the flat to concave or from flat to convex. And it's also different with different types of the lipids. So the overall picture is very, very complex. If you bend the membrane, each lipid type changes, and it's not consistent between the lipid types, and also depends on the bending direction and so on. Schematically, you can see that actually the lipid ordering goes down mostly if you change the membrane curvature, and we can visualize this like this. So in each lipid, we have the proximal and distal part of the tails, and here is a double bond somewhere here. And the distal part changes more in the concave monolayer and less here. And in the convex, the proximal part changes more. So it's kind of strange and weird behavior, which can only be elucidated in the MD simulations. You will never see this experimentally, no tools to see this, but this may be important. And also, if you will look at the error per lipid, if you go from the zero curvature to negative or positive curvature, the changes in the error per lipid may reach like 35%, which is huge change. Now, if you see these huge changes, what happens with the permeability? Well, it depends on which compound is built. This is water. For water, the changes in the EMF are quite minor to go from the flat membrane to the carbon membrane. If we look at the ions like sodium and chloride, the changes are really big. And there's also a shift in the carbs and the change of the height of the barrier. And other drugs, cisplatin and gemcitabine, both anti-cancer drugs, And you can see that the changes are quite dramatic. You should remember that permeability is exponential of this. So if you see such changes here, the permeability will change a lot. But what is a lot? A lot is up to 200 times. So it's really huge. So what we have here, this is zero curvature, positive, negative curvature, and permeabilities for different ions, water, and drugs. And in the parentheses, you see the ratio between the current and the negative. So kind of excess permeability. And here for gemcitabine, it's more than 150 times. For cisplatin, it's a little bit less, but in all cases, it's significant. So basically, the curvature matters, and it matters a lot. Okay, now we know what we can do with the membrane composition, with monomer symmetry and the curvature. Now the main question, is it possible to make the membrane druggable? Let's speak about only cancer membranes for now, because they're the most different from the normal ones. And is it possible to target cancer membranes by some kind of medicines? And can we compute drug membrane interaction and how asymmetry and curvature matters? So is it possible to select the membranes? Yes, it is, but the drug for this is quite special, I would say. So this is not a common small molecule drug. It's kind of nanomedicine, which is based on squalene proteins. How it works? We have squalene, which is a precursor for stored substances in the cell. And this is a long molecule which has a lot of double bonds, and it's completely hydrophobic. It also has 100% bioavailability, and it's absolutely non-toxic, which is great for drug discovery. So you can eat squalene, and nothing happens. So you can consume like 100 grams, no problem. Everything will be metabolized. So it's squalene. And you will covalently conjugate these different substances, for example, these anti-cancer drugs, these antivirals, these neuroprotectors, these antibiotics, or even this small interfering RNA. Then you get kind of very aggregate this hydrophobic tail, for example, here, and hydrophilic head. And these amphiphilic molecules will form nanoparticles in water solutions. And the size of these nanoparticles is about 100 nanometers. Most of them are spherical, but for some compounds, you will see bird shapes like worm-like nanoparticles and funny things like this. But all of them are actually dissolved in water. All of them are stable in the blood plasma. And all of them could be transported by lipoproteins and albumin in the blood. Then they could be taken up by the cell. They incorporate into the plasma membrane, as it is shown here. They switch to the other side of the membrane, so they flip-flop in the membrane. And after that, they act as a prodrug. So the drug is cleaved inside the cell and act inside the cell. So it's kind of drug delivery vehicle in a way, but at the same time, it's very interesting system in terms of the physical. So if you will take gemcitabine squalene, so gemcitabine is an anti-cancer drug, and we will look at how it is uptaken by the cells. First of all, we have a problem because we have a lot of cancer cell lines, but we need to compare with the normal cells. Usually people do this, we are taking some cancer line and we have usual normal cell type like fibroblast or whatever, which is easy to cultivate, and after that they compare. But the problem is that these cells are from different features. So we're comparing apples with oranges, which is not always the best idea. So what we compare the cell lines from the same origin. So if we're comparing MFC7, which is breast cancer, we are comparing this MFC10, which is non-cancerous immortalized cell lines also from breast cells. If we are working with Jurkat cells, which are cancerous lymphocytes, we are comparing with donor lymphocytes. And if you will do this, and if you will look at the uptake of radioactive nanoparticles made of this gemcitabine squalene, you will see immediately that the uptake is much higher for cancer cells with all the pairs. And also depending on the incubation time, it increases, but this gap is actually the same. So cancer cells actually take up a lot more drug if you're using these gemcitabine squalene conjugates. So it's kind of selective, but we don't know on which level the selectivity is. We need somehow to prove that this really happens on the level of the membrane, not on the level of DNA or somewhere inside the cell. So what we did here, we made fluorescent measurements of the membrane order. There are several probes which incorporate into the membrane and which are sensitive to the membrane composition and membrane order. And if your drug also incorporates into the membrane, this probe will sense the changes in the order. Because as we saw before, the order changes a lot. Something is incorporated into the membrane. This is a result. So this is a normal cell line. This is a cancer cell line. For pre-cancer cell, for the lymphocytes, and you can see in both cases there is a difference in the fluorescent response, which means that if you add this drug, something happens to the membrane. So the membrane changes. So this happens on the level of the membrane. And perfect, we know this, let's simulate it. But now the problem is that we don't have a small molecule. We have a huge crocodile, which is made of the squalene and the conjugated part, which is hydrogen. And if you want to compute the PMF, it's almost impossible to work that it is a molecule this size, which is actually comparable with the thickness of the membrane. So the best you can do, you can compute parts of the PMF. For example, you can compute the PMF of extracting this molecule from the membrane outside or inside from each of the monomers. And you can probably try to compute the flip separately. Well, we tried all of these, flip-flop doesn't work. So we spend like 1 year for computing flip-flop PMFs and we get complete mess. It doesn't work. But with the expansion PMF, it works. And here you can see how it looks like. So you have either selective symmetric asymmetric membrane, and you have different curvature. You have either flat, positive curvature, or negative curvature, and a lot of colorful curves, which are different from each other, but it's almost impossible to make sense out of this data. But if you will look at the height of the barrier for extracting the compound, you will see the picture. So first of all, asymmetric, which is normal cells, if you compare with symmetric cancer cells, you see that in the cancer cells, the barrier for exiting the membrane is lower, which means that diffusion to the cytoplasm is actually faster than the symmetric cancerous membrane, and this may explain the higher uptake of the drug. Also, if you consider the whole cell, it has regions with different curvature. You have flat regions, regions of negative curvature, positive curvature. If you will look at the results for positive and negative curvature, you see that the regions of negative curvature will contribute almost equally in cancer and normal cells. But the regions of negative curvature will favor for asymmetric membrane in terms of the symmetric one. So again, for the cancer cells, it will be better in terms of the uptake. So the lesson from this is better uptake in the cancer cells, which is kind of proved by these simulations. So we can actually target the lipid membrane. We can be selected on the level of the lipid membrane. Okay, the next story. This was quite strange compound, which was kind of nanomedicine aggregate of the squalene with a drug. Is it possible to achieve something like this with normal conventional drugs? And here we're coming to unusual membrane effects of existing drugs. So there are a lot of approved, let's say FDA or European approved drugs which could be membranophobic, but these effects are not studied alone. Usually when the clinical trials are performed, there is a test for toxicity and for membrane permeability, but what they call membrane permeability in the clinical trials is not really membrane permeability. They have some cell lines which are intestinal cells, and they test if the drug can pass through this layer of these cells. But this is not membrane permeability. This is most likely active transfer. Let's suppose it's active. So it's not studied before. And the first case is ticagrelor. This is very widespread antiplatelet drug, which is prescribed for cardiovascular events mostly. And it's known to be non-covalent inhibitor of P2Y12 platelet receptor. This receptor have a normal ligand of it's ATP. And if ATP binds, the platelet activates and the cascade of blood clotting actually starts. So if you will block these, you will prevent platelet activation. And this drug was never considered as membranotoxic, despite the fact that it's amphiphilic. If you look at the structure, you see immediately that this part is kind of hydrophobic. This nucleoside analog is hydrophilic. So it should actually act as a membranotoxic compound, but we never studied it. So what we do is we can do simulation of 3 membrane compositions. This is pure DOPC membrane, which is liquid membrane. Then single-membrane cholesterol membrane, which is kind of raft phase. And then the mixture, the ternary mixture of this, which is kind of more realistic way of represents the membrane flexibility and rigidity. So then we incorporate the ticagrelor into each of these membranes. First and short, actually a spontaneous incorporation. So the drug really likes to go inside the membrane. Here you cannot actually incorporate it spontaneously because this membrane is in the gel phase. It's too rigid, so you need to flex it with a membrane by the external force. But if you do it after that, it's heavy inside, so it will stick there forever. And we also compare this with experiments on the whole platelets. So that's what we get in terms of the membrane order. Here you see the DOPC lipids, single-membrane lipids, and the order of the tails. And DOPC, both tails are the same, so you can see the average here. For single-membrane, the tails are different, so we have different plots. But the trend is the same everywhere. If you go from the membrane without any ticagrelor inside to the membrane with ticagrelor incorporated, the order changes. It's quite clear in this case of the DOPC membrane. And in the case of ternary mixture, the change is much larger. So in the real cell, we should expect that the effect will be quite substantial. Okay, that's what we have in experiments. So these are intact platelets. After that, we add ticagrelor and we sense the membrane order with the fluorescent dye, and we say, okay, it increases. If we add ADP, which is activate the cell, it's also an increase, but this increase is from the absolutely different source. If you activate the platelet, you are changing the metabolic synthesis of the lipids, and that's why it changes. Here it's physical, here it's metabolic. And you can also do controls. For example, if you are adding such strange substance as 7-cholesterol, which is cholesterol with 1 beta group, this cholesterol actually changes, it's known from the literature that it decreases the membrane order dramatically. And you can really see this. If you extract cholesterol from the cell membrane, you again see decrease. If you add cholesterol, you make it more rigid and you increase it. So everything is consistent. And it means that if you are adding ticagrelor, you are changing membrane order in consistent way with these conditions. So ticagrelor is really a membranotoxic compound. It changes the membrane order. But now ticagrelor acts on the receptor. This is a P2Y12 receptor. The ticagrelor is a binding site somewhere here. So this compound, it was not designed to act Yeah, because it was on before, so yeah, okay. Yeah. Okay. So if you will look at this compound, it's quite large and it's quite unlikely that it will cross the blood-brain barrier, but it does. It's interesting. And after we found this effect, of course, we tried to reproduce this in MD simulations. Here we did the membrane composition which mimics the cells which are not actually neuronal cells. Since it was COVID time, we tried to reproduce incorporation of this drug into the pulmonary cells. So the cells which are attacked by the COVID virus. It was absolutely useless in terms of medical applications, but it was nice because it was published immediately. So we actually use the COVID hype for this. But this will happen for any membrane composition pretty much. And here you can see that the remdesivir molecules incorporate into the membranes. And if you will cover different parts of the molecules like this, you will see where it resides. This is a distance from the membrane center. So the water interface is somewhere here at 2.5. And the, for example, aromatic hydrophobic moiety is clearly inside. The hydrophobic tail is even more inside. And the hydrophilic moieties are outside. So hydroxy is here on the interface. Nucleoside is here. It cannot move further because of the constraints. But actually, everything is quite consistent. And this is the head groups and the tails. So this is a tail. And the head groups are somewhere here. So actually, what you see is pretty much expectable from the physical point of view. So the thermodynamic works. Nothing surprising. The only surprising thing is remdesivir resides into the membrane. It's happy there. And this is another unexpected membranotropic drug, which nobody was thinking about. And now it's an interesting question. Okay, it incorporates into the cellular membranes. Is it possible that it incorporates into the viral membranes? Because it's possible that it has some direct effect on the viral membrane and somehow influences the fusion of the membrane of the virus with the cellular membrane. So far, we don't know, but it's possible. Okay, so I'm pretty much have 10 minutes, so I'm ahead of time, but okay, so the conclusions. First of all, you should understand that the membrane should be considered as a first-class entity in drug discovery. It's not possible to treat the membrane as kind of unfortunate permeation barrier, especially if you're working with amphiphilic drugs. You have no choice. You have to consider interaction with the membrane. Lipid membranes by itself are druggable in a way without involving proteins. So it opens some new treatment modalities for cancer and possibly for some precision medicines and other therapies. Existing drugs may have unexpected membranotrophic effects. So if you found some molecule, which is a drug candidate, and this molecule binds nicely to some protein, it's probably wise to see if it binds to the membrane at the same time, because you may find some unexpected drug repurposing or off-target usage. You may find unknown adverse effect of this drug, or you may even find some possible dual action on the membrane and the protein itself. And finally, if you are working with the membranes with MD simulations, membrane and symmetry and membrane curvature really matters. So if you ever try to do drug permeability, I don't advise doing this because it's quite boring and you should avoid it as much as you can. But if you are doing this, you should consider a symmetry and curvature of the membrane. And MD simulations of the flat membranes are not enough in this respect, which adds another layer of complexity. Yes, so this is pretty much it, and thank you for your attention.
So some questions from the audience? Yeah.
I can sort of grasp how embedding more of embedding change the behavior of protein that are embedded for anything that I need to get information there. And I didn't see how the hemodynamic motion for the limited section. So I really can see that because in any sort of tissue or in the biology case, total amount of cell membrane surface is going to be associated huge. So how big of a concentration or how much of these like small membrane surface changing molecules will you actually need to give to the patient to have comfortable effect?
Yeah, this is a very nice question, actually. These concentrations seen always appear even without the membranes. If you consider the normal water-soluble drug, like aspirin, for example, if you will, you can take up to half gram of aspirin, as far as I remember. How you would measure how much is actually on the level of the cell? So aspirin molecules you have in the organism per one protein molecule of interest. It's almost impossible to get, it's quite hard. It's the same for the membranes, but for membranes, it's easier in the sense that your molecule accumulates in the membrane. Amphiphilic molecules go inside and they will stay here for a long time, at least for the time of membrane recycling, which is minutes. So you're pretty much sure that if you see the biological effect of this drug, it's enough to accumulate around the receptor. You cannot tell for sure how many. So either you have one molecule per protein, or 10 molecules per protein, or something like this, but you are sure that there is something and it is significant. Then, ideally, in the ideal world, in MD simulations, you have to do the concentration dependence. So you have your system with 200 lipids, you are adding either 1, 2, 5, 10 ligands, and you see what happens. That's what we tried to do with this. For example, yeah, here, this is for 5 molecules, as far as I remember. But funny enough, if you will leave only one of them, this doesn't change a lot. Because I didn't mention this here. These curves actually, what's the difference between blue and red? Blue is the first coordination shell of the lipids around the molecule. Red is everything else. So it's near and far to the ligand. And actually what happens, you see a change near the ligand and smaller change in the parts of the membrane which are far from your ligand. So if you add 10 molecules, and if it is enough for these first coordination shells to collide, then you will see some cumulative effect. If not, you would not see this. So all this is quite complicated.
Other questions? Yeah, from online.
It is very useful if you want, for example, to bend the membrane and to simulate the membrane shape, because it's much, much faster. But in terms of drug-membrane interactions, the problem is how to cross-grain the molecules, the drug itself. It's possible. The Marin group with Martini force field is actually playing with this for a few years, but I don't trust the results that much. Because statistically, if you are cross-graining 1,000 compounds, you see quite consistent trend. So it in a way works. But if you have your ligand, which your PhD is actually devoted to this ligand, you are not considering thousands of compounds. If your ligand is out of the trend, and it's 50-50, it could be, then you are out of luck. So you have to tune it somehow. And in order to tune the cross-graining, you need to compare this with a fine graining, with atomistic. So anyway, you have to do atomistic first. Then what's the reason of cross-graining? So I would say in drug discovery, it's pretty much useless. Some people may actually argue with this, but this is my subjective position.
Since the membrane is such a mobile entity, that we know there is possibly invading this, like, and groups or something, how are the simulations made to ensure that when you have a correct prototype for a drug, it stays where you would like to stay?
Well, there are two aspects here. If we are speaking about composition, you cannot do anything. You are simulating the composition which you want. If there are several compositions, you are doing just separate simulations. In terms of the membrane curvature, for example, if you're working with spontaneous curvature, then it fluctuates. So your drug will eventually find the place where it is happy, and you will see the distribution according to the curvature. But you will wait for a long time for sure. So better to do simulations of the flat membrane and the curved membrane, and after that you will have some feeling about the behavior of the drug, and you will extrapolate to the membrane this variable properties. This is the best way to do this. So there's not a silver bullet. I mean, you cannot simulate the cellular membrane, which is millimeter scales.
How to choose which simulation would be better?
Good question. Usually, if you have some measure of the membrane roughness, like AFM measurements, for example, you can roughly estimate the amount of flat membrane and the curved membrane and kind of average curvature. But it doesn't work most of the time. It only works on some cell types. It was one question over there. So let me go back to this. You're speaking about this one, right? So here you are scaffolding the membrane. So the shape of these blue doomy particles actually dictates the membrane, the curvature, and the shape. So you can scaffold as you want. But this is fixed in space, so it's not fluctuating. So it fluctuates in terms of breathing modes, and the lipids are diffusing, of course, but the shape is fixed. It's the same here, but you are not using the doomy walls, you are just restraining by pulling, but it's pretty much the same.
I want to know, beside that, the shape amplification, that it could be useful to assume that there could be a structure amplification. I mean, things are lipids inside the membrane that could be useful, like really like oil, the solution that is more easier to treat the molecular dynamics.
Well, you. Well, it depends what you want to achieve. For example, if you are computing the partitioning of the drug, usually you are doing this in octanol water. You don't need the membrane for this. And since you have experiments for octanol water pair, this is a fair comparison. If you want the membrane permeability, then you have to do the lipids. There is no way. For example, here, I will come back to this one. Where is this? Just a second. Yeah, this one. For example, look here. The black curve here is pure DOPC. So it's just one lipid type. And these curves are realistic membrane composition. And you see the difference. The difference actually in permeability is 5 orders of magnitude. So if you want really to get the drug permeability, which is somehow comparable with what you get in the clinical studies or in vitro studies, you have to be as precise as possible. Because if you miss one lipid type, you can be off by 2 orders of magnitude easily. So, yeah.
Thank you. Other questions? Yeah.
It depends on the protein target very much. For example, if you're working with mechanosensitive ionic channels, for example, then mechanosensitive ionic channel works in exactly this way. When the membrane binds, the channel either opens or closes. So the curvature matters, and it matters a lot. If you're working with protein which is not sensitive to this, like GPCR, for example, then probably not. but it's hard to tell because some proteins are also asymmetric if the shape of your protein is not cylindrical and the volumes of the protein globule in the outer and inner leaflets are different. Then curvature may play a role because you're compressing or actually extending the protein itself to the different extent. So it's hard to tell. It's necessary to look at the protein.
Other one questions? No. Well, I think we can stop at this point. We have enough time for lunch. Replenish your energy and continue the tutorial.